Hi everybody, welcome to the next lecture on audio coding. Today about audio coding for communications applications. My name is Gerald Schuller. So first, what are the applications? So in general, audio coding or compression is used in multimedia applications, as we know, or storage or digital broadcasts like digital radio, for instance, Sirius XM satellite radio in the USA, or DAB Plus for terrestrial radio in Europe and many other parts of the world. And here you can see this is broadcast, right? So here delay is not critical. You just transmit something and there's a delay on the path from the transmitter to the receiver, but it doesn't really matter. So examples for this application are the well-known MP3 or MP24, AAC, then there's Dolby's AC3 or Alcatel-Lucent's MPEG. But neural networks offer higher rates and also lower delay. For instance, high-speed internet access, higher rate of wireless services. Here I should mention, for instance, IP version 6, which is becoming more widespread in the internet. And this internet IP6 also has this quality of service option for lower delay. And in this way, packets which are time critical are forwarded more faster in the internet nodes. And on the wireless side, we have 3G and lately 5G. Especially 5G is also made for very low delay. So 5G particularly is made for real-time communications or suitable for real-time communications. And then of course we can have local networks which can also be made to be very fast for time-critical data. So here we want to talk about those applications for communications which are time critical. For instance, for high quality teleconferencing, for instance, Apple's FaceTime or Jitsi, which we are using, or also reporting for radio and TV stations using wireless networks. But delay-wise, most critical is the virtual presence, for instance, for musicians playing together over long distances. So you can imagine when you have musicians, they need to play in synchrony, especially if you have timing critical instruments like drums or castanets or such. So there the delay is really critical. Or if you have concerts with wireless microphones and speakers. For instance, if you have musicians playing and they have wireless microphones and maybe also wireless earphones, then the delay is very critical. So the desired delay here is less than 10 milliseconds. So experiments showed that we need to be less than 10 milliseconds for drums or castanets, maybe even less than 6 milliseconds. And this is what we call ultra-low delay. So these are our goals. We want to have audio coding for communications with an ultra-low encoding-decoding delay, less than 10 milliseconds. So compare that, for instance, with MPEG, AAC, ELD, which we already talked about. This goes down to about 15 milliseconds at 48 kilohertz sampling rate. So that's not quite low enough. So for those critical applications, we need to have a different approach. We still want to have high quality for music and speech. So particularly for these applications where musicians play together. And also the bit rates should not be too high. So the goal would be 50 to 100 kilobits per second. But here we also need to keep in mind that lower delay usually means higher bit rates. So the problems that we have is that in conventional audio coders, we have a good audio quality, but a very high encoding-decoding delay, usually much larger than 100 milliseconds. And as I just mentioned, the AAC ELD has a delay of about 15 milliseconds at 48 kilohertz. Speech coders are also made for communications, but not for music, right? They have a low encoding-decoding delay on the order of 10 to 50 milliseconds, which is suitable for communications applications where people talk on the phone or in video conferencing. But they don't have high quality audio and don't perform well on non-speech like signals like music or room noise. Yeah, so here again, this principle of conventional audio coders. Here you have this filter bank. After the filter bank, you have quantizers in each subband controlled by the psychoacoustic model, which computes the masking threshold based on the current signal. And after quantization, we have the indices, which are entropy coded and sent to the decoder, where you then have the synthesis filter bank and the reconstructed decoded signal. Yeah, and in psychoacoustics, you have temporal effects and also spectral effects. So our models are usually dealing with masking in frequency, which would be the second picture here. So here you would have an idealized spreading function for a sinusoid. But you have a similar effect also across time, as we know. So here we would have a pulse, and this is then the masking threshold. So here we would have the post-masking and here the pre-masking or backward masking. So this is actually something that is also difficult to do using a high number of subbands, as we saw when we have castanets. For that reason, we switched down to 128 subbands. So 128 subbands turns out to be quite suitable for even the most time-critical applications. And this is also what we then want to build upon here. So the major sources of delay are the system delay of the analysis and synthesis filter bank, particularly if you have 1024 subbands. Then we saw that an MDCT would have a system delay of 2047 samples. So that includes the blocking delay and the delay coming from the delay matrix. Yeah, plus we have buffering from bitrate smoothing. This comes from the switching when we have castanets, mostly. And this is also a problem, right? We would like to get rid of this buffering for bitrate smoothing, or at least make this buffer as small as possible. Yeah, and previous approaches use low delay filter banks, which we saw, like in the MPEG-4 AAC-EL decoder. It uses a low delay filter bank, and it also has a somewhat reduced number of subbands, right? It's around 500 subbands instead of 1024. So that also reduces somewhat the compression performance. So what can we do? Yeah, so high coding gain requires a high number of subbands. And for low delay filter banks, the delay is lower bounded by the downsampling factor, which is equal to the number of bands. So here we hit a lower limit. And in MPEG-4 AAC-ELD, so here this should be just 1A. Okay. We have a somewhat reduced coding efficiency, a somewhat higher bitrate, and also not an ultra low delay. So we have 20 milliseconds at 32 kilohertz sampling rate. And the reason here is that the subband coding leads to a trade-off between coding efficiency and delay. So the new approach tries to replace the filter bank by a predictor. So it was shown by Giant and al. In this book that subband coding has the same asymptotic gain as predictive coding. So basically that means we can replace subband coding by predictive coding. And at least ideally we should be able to get a comparable compression. But predictive coding has the advantage of a lower delay. So that is suitable for our goal. Yeah, the problem is the output of a psychoacoustic model is a time frequency description, So it's not so suitable for predictive coding. So the approach here would be to separate the stages for the application of the irrelevance reduction, the psychoacoustics, and for the redundancy reduction. So for the redundancy part, we need the many subbands. Not necessarily here for the psychoacoustics. Then we apply the psychoacoustic quantization noise shaping in a separate block for the irrelevance reduction and use lossless predictive coding after the quantization, which would be the redundancy reduction. So we have two blocks. First, application of the psychoacoustics together with quantization according to the masking threshold. And then we have a lossless predictive coder after it. So instead of having many subbands, we might have a long predictor. So we would use the same predictive coding that we already saw before, right? So we could just use some lossless predictive coder, provided that it has sufficiently low delay. So here's an overview, a block diagram of this approach. So here on the left-hand side, we have the encoder. Here in this dash block, we have our prefilter, the irrelevance reduction. And we can see we have the audio input. We still have this psychoacoustic model. So this psychoacoustic model has an MDCT filter bank in it, or an FFT filter bank, with the reduced number of subbands. So we use the 128 subbands that we already know from the mode for castanets or attacks. So there we know that it's sufficient for even the most time-critical signals. And we apply that here for the psychoacoustic model. So this is based on 128 subbands. And this outputs a masking threshold. And this masking threshold controls a prefilter such that it shapes the input signal, the audio signal, such that the resulting masking threshold is now flat. So basically, the prefilter has a frequency response which is inverse to the masking threshold. So that also means when we have now a constant masking threshold after this prefilter, then we can simply apply a constant step size fixed quantizer, Q. Right? So this Q produces the same quantization noise for all frequencies at all times. And after this Q, we have a different audio signal coming out here, and we can apply some lossless compression to this audio signal. And in the decoder, we have the reverse steps. We have lossless decoding to reconstruct the special audio signal. And then we need to apply this post filter, which is now undoing the pre-filter effect. So that means this post filter also needs to have the side information of the masking threshold coming out of the psychoacoustic model. But instead of having the pre-filter like the inverse masking threshold, the post filter has a frequency response which is shaped like the masking threshold. Right? So after the lossless coding step, you again have this quantization error shaped constant over all frequencies, and after the post filter, hence it is shaped like the masking threshold. And this is the goal that we have after all. Right? We want to have the quantization error that we introduce shaped like the masking threshold such that it stays below the masking threshold and hence becomes inaudible. Yeah, so here again what I said, pre and post filters shape the quantization noise over frequency and time. Right, so when it's also shaping it over the time. When we look back here, there should also be a gain factor here, which I didn't show, which is basically part of the pre-filter, which also applies the suitable gain to have always the same quantization step size. The post-filter is inverse of the pre-filter. The pre-filter normalizes the signal to its psychoacoustic masking threshold. So after this pre-filter, the masking threshold is constant over time and frequency. Then we can apply a simple uniform constant step size quantizer, a simple rounding operation, for instance. And then we have this added benefit of a more precise control over the quantization noise shape, particularly over time, than the conventional approach, right? Because we are not doing the downsampling by this high factor here. Yeah, and this shows a possible pre-filter structure, right? So we need a short delay for synchronization with the psychoacoustic model. So there's still some delay in here, this delay here, and that's because we need to synchronize the masking thresholds coming out of the psychoacoustic model with the signal. Right, so we have the audio input, we have our analysis filter bank, for instance an MDCT or an FFT with 128 subbands. Then we apply the psychoacoustic model. This outputs the masking threshold, and here this masking threshold is then translated to linear predictive coefficients or line spectral frequencies and a gain. Right, so this gain is applied here first, and then this linear predictive coefficients or the line spectral frequencies are applied to a linear filter, which is here made like a predictor. And this makes sure that we have the inverse of the masking threshold here in the frequency domain. So remember this, a predictor, an FIR filter used as a predictor has a frequency response which is basically the inverse of this frequency response of this FIR filter. Yeah, so after this we have the signal normalized to its masking threshold coming out here, and then we simply apply this quantizer to obtain the pre-filtered quantized signal. Yeah, so the properties here is, first, the disadvantage is computationally complex, right? Since we don't do any downsampling in the signal path, we have to operate all the operations at the full sampling rate. And that's kind of complex. But the advantage is we have no inherent delay except for the smaller filter bank for the psychoacoustic model, the delay coming from that, which makes it suitable for communications applications. So here you can see the effect on the quantization noise shaping. So here's an example. So this top line here is the frequency response or the spectrum of our audio signal, which you can see here. And so this is the I compared to the masking threshold. This II here is the masking threshold as computed by the psychoacoustic model. And the frequency response of the post filter, which shapes the quantization noise, the three I's, can be seen here. Right, and you can see it's actually a very good fit, except here maybe at very high frequencies the fit is not so great, but that's also where the ear is less sensitive, so that should work fine. Yeah, and finally, we need the redundancy reduction after our quantizer from the pre-filter. So the irrelevance is removed after the pre-filter and the quantizer, and then a lossless compression is needed for the perceptual lossless coding. So here we just take a lossless coder, a lossless audio coder, which features a low enough delay. Yeah, so we can also control the bit rate using this scheme by just introducing a factor after the pre-filter and before the quantization. So here usually it would be 1, but a factor less than 1 leads to quantization noise above the threshold of audibility but a reduced bit rate. So imagine when we have a factor smaller than 1, we make the resulting signal smaller, and that means we have less of the signal left after quantization. So compared to the signal appears smaller compared to the quantization step sizes. But also that makes the encoding easier because we have smaller indices to encode. Yeah, so by adapting the attenuation factor and iterating the lossless coder a target bitrate can be approximated. So if we need to have a certain target bitrate, we just adapt this factor here. So here I'm using this factor. Later in the software I'm using %, then the factor 1 would correspond to 100%. Yeah, so now for my Python example. So this example is from our class book, Filter Banks and Audio Coding, Compressing Audio Signals Using Python, from Springer in 2020. And the complete software is in our GitHub repository, TU Ilmenau AMS Python Audio Coder. So the example you can just download from our GitHub. Yeah, so first let's implement the Psychoacoustic Pre-Filter. So to simplify things, instead of a linear filter in the time domain, we implement this filter as scale factors in the frequency domain of the MDC subbands, which we need for the filter bank for the psychoacoustic model anyway. But it only has 128 subbands for the low delay. Right, and this allows us to reuse the software that we already have for our audio coder. So we simply use our previous coder function for the scale factors, for the quantization and dequantization. So in this way, the result is basically a simplified audio encoder and decoder with a 128 subband MDCT, but without the scale factors in the decoder. Right, because we want to normalize the signal to its masking threshold, so we just omit this scale factor multiplication here for the pre-filter side. And of course without an entropy coder, because that's part of the lossless predictive coder later. Yeah, so we have this function Psychoacoustic Pre-Filter, and that is the Python code for the Psychoacoustic Pre-Filter. And its input is the audio signal X. So here you can see it. Here's this function, Psychoacoustic Pre-Filter. First argument X is our audio signal. Then Fs is the sampling rate. And here is the quality factor. Default is 100%. And its output is the audio signal normalized to its masking threshold, which we call xpref. And also the quantized scale factors MT_bark quant. Remember, this is what we need to transmit as side information to the decoder, so we also need to output it. So here you can see it. Here we set the number of subbands, 128. Here is the number of subbands in the bark domain for the precision of our psychoacoustic model. So again, we use 64 subbands in the bark domain. And remember that this number also influences how many bits we need as side information to transmit the threshold to the decoder. Here's the sine window for the MDCT, the standard sine window. And here's the analysis MDCT and normalization to the masking threshold and quantization. So here you can see the function for the MDCT. Right, so this MDCT, so here we apply the MDCT together with the psychoacoustic model and the quantization. So it's an all-in-one function here, conveniently. And it takes the signal X as input, the sampling rate, then the window function, the number of subbands, the number of bark bands, and here the quality. So very convenient. And out comes the quantized subband values, YQ. So this YQ is then an array containing the 128 subbands with all the subbands in each, with all the samples in each subband, but quantized. So this YQ is basically the indices that we obtain after quantization. Y is the non-quantized version of the subbands, which we don't need here, and then bark quant is the quantized scale factors. Yeah, so we don't really want the subbands as output of our Pre-Filter. So that's why we apply now the synthesis filter bank. Here you can see it, an MDCT synthesis filter bank, but without applying the scale factors as you would do in the standard audio coder. So here we just transform it back to the time domain, and xpref is then our signal back in the time domain. And we return this xpref in the time domain and also the site information, the scale factor, the quantized scale factors. So that's why we have both the MDCT analysis and synthesis here, because the output of our pre-filter is a time domain signal, right? Unlike standard audio coders, where the output is subbands, here the output is a time domain signal. Yeah, so then we need the post filter. For that we have the function Psychoacoustic So this is the corresponding psychoacoustic post filter. Its input is the pre-filtered audio signal xpref, which we just generated. Again, the sampling rate fs and the scale factors, the site information, the quantized scale factors MT_bark quant. And its output is the reconstructed audio signal xrec with the quantization error shaped like the masking threshold of the audio signal as desired. So here you can see the function Psychoacoustic. First input is the audio signal from the pre-filter. Then here we have the sampling frequency and here the quantized scale factors. Yeah, so first again we set the number of subbands for the MDCT. Again 64 subbands in the bark domain, standard sine window, and first we do apply the MDCT analysis to xpref, the signal coming from the pre-filter, to get YQ. So basically we get back the YQ that we had in the pre-filter. But now we need to remove the first and last block because that's what the MDCT appended. Right? It makes the signal longer, but it needs to fit to our masking thresholds. So that's why we need to remove them, the first and the last one here. Yeah, and now we do the denormalization of the masking threshold. So now we apply the masking threshold in the post filter. And we do this with this function MDCT syn dequant dec. So here we have this dequantization in the decoder and apply it to the subbands YQ, the quantized subbands. So here we have the indices from the analysis. We apply our quantized scale factors. Oops. We apply our quantized scale factors here. We have the sampling rate for the psychoacoustic, for the psychoacoustics, for the bark scale. Here the sine window, number of subbands, and here the number of filters in the bark domain. Yeah, and this reconstructed signal is then returned as the reconstructed audio. So again, observe that we have both MDCT analysis and synthesis. So here, first we have the MDCT analysis, and then we have the synthesis as part of this more complex function, which also includes the scale factor dequantization here. Yeah, so then we put both functions into this file psyac pre-postfilter.py and add this main section, which contains a demo with the original file fantasyorchestra.wav. Right, and I chose this file because we can freely download it from freesound.org. So just go to freesound.org and Google for fantasyorchestra.wav. Maybe I can show it. So we can just go to freesound.org, open a browser, and what we get here is Freesound, and then we can Google for fantasyorchestra.wav. copy, search here, and what we see here is fantasyorchestra.wav. So this is the file that I used, and you can download it. You might have to log in to download, but it's easy to create a login for this. Yeah. So then we can download this file fantasyorchestra.wav into the same directory as the file Psychoacoustic Pre-Filter.y, and then we can start it with this command line, Python 3 Psychoacoustic Pre-Filter.py. And there you will get a demo with synthetic speech announcements and also spectrograms and plots. And plots. Right. So also in the terminal you can see the printouts that it makes, and it actually shows that it's slower to compute. So it's not as fast as subband based audio coders, and that's because it's completely or mostly in the time domain, so it's more complex. So this is what we will see. First, the spectrum of the original signal. So horizontally you can see the blocks here, the block number, oops, and vertically you can see the normalized frequency from 0 to pi. So this is 3.14. This is Nyquist, right? And you can see here in the beginning there's not much, and then you have some music which has some high frequency components, and in the end it fades down. Then we apply the pre and post filter. So the masking threshold of the different audio blocks are shown here. These are concatenated and output also as the WAV file by the pre-filter. So here you can see the masking thresholds in the MDCT domain, and here you can see the bark subbands. Right, so this is still in the bark subbands, and you can see here at the high frequency end we have a strong increase in the masking threshold, and that comes because our ear becomes less sensitive at high frequencies. Similar at the very low frequencies, right? So it also is elevated here. And you can see so many curves because you can see one curve per block. And since we have thousands of blocks, that's why we have so many curves. Yeah, but you can see they are kind of limited, right? So they are ranging in index value between in value between say 0 and 50 or 60. So it's not that much. And this is the result of the output of the pre-filter. Observe that only a few quantization steps are actually used, which makes it easy to compress. So here you can see it. So here you have 1, 2, 2.5 is not really used, right? It's just the scale here in the end. You just have integers here used. So this would be 3, 4, 5, 6. And only in the end you have somewhat higher values. So that's very different from the original audio signal, which has values between -32,000 to +32,000. Right? So here we have just values say between -10 and 10. And that's what it makes it so much more easy to encode. So this is where we actually gain a lot of compression when we apply a lossless audio coder to this signal, right? Because it's so much smaller. And then we can actually listen to it, and we will find that it sounds like a very soft, high-passy, noisy signal. So very soft because it only has a few steps here. Actually, without amplification, you would not hear it at all. But if you amplify it, it's very noisy and also high-passy. Yeah, and then the spectrogram after post-filtering. So this is the output of the post-filter, the reconstructed audio signal. And here you can see that now there's more noise here at the very high frequencies. And remember, this is the region where the ear does not hear much anyway. So we can easily put some noise here and the ear will not hear it. Yeah, very similar here at the very low frequencies. And here in the middle range, there's not too much difference. There's some difference, but not too much. So there we can also hear that it sounds almost exactly like the original, despite the larger visible differences in the spectrogram, particularly at high frequencies. And these are the regions where the quantization error is shifted to. Right? So here we hide the quantization error basically coming from our relatively coarse quantization. Yeah, so before we come to this one, I actually want to start this demo here to show it to you. So copy, and now I open my terminal where I have my Python files and also my sound file. So here we can say ls fan star. Oh, interesting. ls star.wav. Okay. Yeah, I need to go one down. Python audio coder. So that's where basically I used git clone to obtain the entire GitHub directory in this local directory Python audio coder. Right, so that's very convenient. And then I downloaded this file into this directory. So let's try it again. Yes, so here you can now see it, fantasyorchestra.wav. Here it is. And then we can execute our program, see what it's doing. Paste.
Pre- and post-filter demonstration.
Yeah, so you heard this synthetic voice announcement. Here's the spectrum of the original that we just saw. Now we are computing the MDCT for the sound file. And you can see it takes a little bit. It takes a few moments. Takes a long time. Yeah, so part of this is also that the MDCT here only has 128 subbands, which is also more complex to compute than a higher number of subbands. Yeah, so now we saw masking threshold calculation was relatively fast. Now we do the quantization according to the masking threshold. It's again a little slower. So here basically we have to use a for loop to go over all the subbands. And here you can see the resulting masking threshold, which were computed. And this is the picture that we just saw. So here we can see the masking threshold in the bark subbands for each block that the MDCT outputs. Yeah, now it continues. Again, it takes a while. Now it computes the synthesis MDCT. It should compute the synthesis MDCT, hopefully, which again takes a while since it's only 128 subbands. So let's see. Right. So here was the shape of the quantized subbands. Actually, it was the subbands, the quantization that took so long. Because it uses for loops. And here's now the inverse MDCT. Now it computes the inverse MDCT to obtain the output of the pre-filter.
Original signal.
Original. Yeah, and when you listen to the original, it also doesn't sound completely clean, and that also makes it somewhat more difficult to encode. Here's the psychoacoustically pre-filtered signal. As we just saw, you can see it has very low amplitudes, just very low levels.
The amplified pre-filtered signal. Reconstructed signal after the post-filter.
Yeah, so this was the reconstructed signal. I think it sounds almost exactly like the original, with only small differences. So that shows it works. So even though the spectrogram of this post-filtered signal shows clear differences, we don't really hear the noise that is added here. So that was successful. Yeah, so we can also take a look at the files that were produced using ls-lt for long and time. So here it outputs the latest files first, and I input it to more to get only one screen at a time. So here we can see it. Q. So we have this fantasy orchestra masking threshold.wav. So we can actually listen to the masking threshold because it's a WAV file, right? So you can see it's a WAV file with 500 kilobytes. Here we can see Fantasy Orchestra Pref is about 1 megabyte, but it's not compressed, right? We need to still apply lossless compression here. So now let me play it using a play the masking thresholds, just out of curiosity to see how it sounds. It's actually not something to listen for, but we could. Yeah, and this tone actually is the block rate, right? Remember, we have a complete masking threshold for each block. So we have some sort of periodicity in our signal, and that gives us this tone that we just heard, right? It's, yeah. And that also means we can, since this is a WAV file, we can also apply lossless predictive coding to this file to get a reduced bitrate. So that's the advantage of both having being a WAV file. We can apply lossless coding to both of those files. Although it would be beneficial to have a specialized lossless audio coder for the masking thresholds because of the special shape or the special statistic it has. So it's not like a typical audio signal. Oh yeah, and I wanted to also play the non-amplified version, copy. So this is the original pre-filtered audio signal, a play. So you can hear it's very soft. It's hard to hear. You hear it a little bit, but it's very soft. And that's the point, right? We just have a few quantization indices here, ranging from roughly -10 to 10. So that makes it very soft. Yeah, so again, we can now take those two files and input them to a lossless audio coder. Right, and this basically leads us to our ultra-low delay coder with pre and post filter. To obtain an ultra-low delay audio coder, we just need to losslessly compress the pre-filter output with a scale factor with low delay. Right, so we have those two. Maybe I call this losslessly. The output along with the scale factors, right? And we can use the predictive lossless coder we saw for the pre-filtered audio signal. So let me go back full screen here. So this is what we previously saw for audio signals. Now we apply it to this pre-filtered audio signal. But for the scale factors, a specialized lossless coder would be beneficial. But also the same predictive lossless coders could be used, as I actually do in the book. And in the book, I actually have another example for this ultra-low delay coder, a demo, which you then can execute and see what it's doing, and also check out the bitrate that you obtain. So I encourage you to do that yourself using the code from the GitHub repository. So the function for it in this GitHub repository is lossless predictive audio encoder and lossless predictive audio decoder, which we would apply here to the pre-filtered output and also to the masking threshold WAV file. So we simply apply this predictive audio encoder and decoder to those two files. Yeah, and that leads me to my conclusions. We saw that predictive coding can be used to obtain ultra-low delay audio coders, and we obtain a delay of about just 6 milliseconds, which is less than the desired 10 milliseconds. And the subjective audio quality is comparable to a conventional high delay coder at the same or somewhat higher bitrate. So actually the GitHub repository also contains a conventional audio coder which you can try out on the same file and compare the quality, and you will find it's actually comparable. But actually the bitrate that we obtain is actually a lot higher than from the conventional coder, and that's because we don't use a specialized lossless coder for the masking thresholds. Yeah, so mainly the price here is higher complexity, as we saw. It takes a long time to compute. And it can also be used to obtain high audio quality, unlike speech coders, right? So it's just a matter of bitrate, basically. Okay, yeah, and this should be it for today. Thank you for your attention, and then see you next time.